Hello, it's Duncan. When we left our hero, he had discovered that the external pricing service that Gilded Rose uses is too slow to price all the stock in an acceptable time. It would be fast enough if we could make lots of HTTP requests at the same time. So basically we need something to convert the items in a list, which is our map operation, in parallel. That's a parallel map. And in this episode, we'll write 4 of them using different concurrency models in Kotlin on the JVM. Let's remind ourselves what the problem is. I've got the server running here, and here's the browser viewing our stock list, and I'm just going to refresh. And you can see that little wheezy thing there, and then finally it loads. Let's do it again. 1001, 1002, 1003. Okay, so maybe 4 seconds for the whole page. Definitely slower than it used to be, I think. Now, a long time ago in episode something, we wrote some tests to run against the actual value of server. And this is where we found that it was sometimes failing. So we still had this test. We checked it in. We don't run it normally because, in fact, this one doesn't actually have any assertions. It just reports to the console how many failures we had. Let's try running this and see how we do. Well, that was 50 seconds. I don't know how long it was taking to run before, but I'm pretty sure had it been 50 seconds, I would have cut this down from 500. So something's definitely gone slower with the value of service, but note also that it hasn't failed. So it looks like after our bug report, they found a way to make it work reliably, just not quickly. It's a shame this has happened just as we started using their service, but these sort of coincidences seem to be common, so let's see what we can do about it. First of all, I think we'll cut this down to 50 iterations. That should mean that it runs in about 5 seconds. Let's have a look. Well, there we go. It is at least linear. And worth checking again that we still have no failures, because if failures are random, then we might just have had a lucky break. Right, the nice thing about map is that it should be quite parallelizable, providing the thing we do in the map doesn't affect other calls. And here we're just invoking the client, which will go across the network, but we don't expect the price of any one item to depend on other calls to the pricing service. A really easy way to run a parallel map on the JVM is to use the Java Streams API. We can't convert this range to a stream, but we can convert it to a list first of all, and then a stream out of it. And then stream has a map, and at the end, we can call toList. Right, let's try running this and see whether it works. Remember 5 seconds before. Now it's still 5 seconds, but we're using streams to do the map rather than Kotlin's map. How do we get parallel? Well, we call parallel there. And that's it. Try again. And now we're down to a second, which is brilliant. There's just one problem, which is that parallel streams aren't really suitable for running in servers. They use the fork join threadpool, which we don't have any control over, and might end up using threads that we need for other things. This has been a good proof of concept, though. We know that we can get a speed up by making requests in parallel. So now let's step back and look at other solutions to this problem. So I've created parallel map tests here in our foundation package, which feels like a good place to put it. And what I think we'll do is we will write some tests to characterize the thing that we just wrote, because I think the Java Streams version is pretty likely to be correct. Once we've got tests that we trust running against that, then we can apply those tests to different versions that we'll write. For these sort of things, I like to step away from the actual problem, which is talking to the value of server, which is complicated by networks and so on, and write as close to the metal unit test as we can. Map is a function that takes a list of things and returns another list of things. Those things may be different types, and I like to use strings and ints whenever I can. So let's sketch this out. So our input is going to be some sort of list of, say, string. And if we had that, then we could say our output, which is a list of int, is input dot, and we'll use a plain old map for now. And let's say it's it dot length. And we can write at least one assertion, which is that the output size is the input size. Now, I think that will be true for 0 strings. And is. Let's up the ante with a bigger input. What I think maybe we'll do is we'll have 1 to 100, and we'll map it to string. Now then, we expect that the first element, in fact the first 9 elements, will have 1 character in them. So we'll go to 8. Then 9 should be 10, which is 2 characters. And that should be true all the way up to 98. And then the very last one, which is at 99, should have 3 characters in it. Let's see whether that's true. Well, it is, and that seems like quite a good way of easily testing quite a bit of data. Now, at the moment, this is not a parallel stream version. This is just the Kotlin version. So let's mark it away. And I don't know why that was ever a val. Right, now we're using it.length here to keep us honest that we are actually computing something, but that's way too quick to test our parallelism. So let's give ourselves a thread sleep in here. How long should we sleep for? Well, we're mapping 100 times. So if I put 50 milliseconds in here, we should be done in 5 seconds. Let's see whether that's true. And that's close enough for government work. So that's our baseline. It's not running parallel, and it's taking 100 times 50 milliseconds to run. Now, it's notoriously difficult to assert on the amount of time something takes, but we can attempt that here. What we can do is we can split this variable definition here, and then time the run of just that block. And we know that it's got to be at least 5 seconds in this case. Okay, let's run that. Good, so that's our baseline. Let's duplicate this for our parallel version. And this is parallel stream version. And in here, we're going to say input stream parallel map. And then at the end, we have to collect to list. Let's try that. And now that fails. We hope it fails because it went too quickly. Let's have a look. And that is true. It took less than a second, which is what we wanted. Now, what with garbage collection and other things going on this machine, it would be hard to specify a tight minimum time. But I think we might say that, well, we expect this to run in less than 2 seconds. That should make this pass. Excellent. Now we want to extract a function, ParallelMap stream, for this functionality. So what we can do is we can extract a method and call it ParallelMap stream. And now take that and move it to the top level and make it public. Now we can make this input into the receiver and take this lambda and make it the parameter. And then finally, we don't want this just to work on strings and ints. So we can go over to the string and say, refactor this and make it a type parameter. That string, t will be fine. And then yes to that will replace that t. And we don't want to constrain t to be a string, so we can just delete that. Remove the name, and then for the int, do the same thing. Int wants to be r for result, but doesn't want to be constrained. Okay, IntelliJ is slightly broken that refactor here, so we can just remove that type parameter and run. Good. So if we look at our 2 tests now, we can see that they are pretty much identical. The only difference being the map version that we use, this map or that map, and our test about the time. That's the point really. We want to show the behavior was the same for our different parallel versions as the Kotlin version. It would be nice then if that test was all in the same place. So let's try and extract a function that represents our whole test. To do that, we're going to try and move this bit outside this bit, because this bit is the bit that's in common. So if we could move the name of this function effectively out, then we could extract the common code. This is a bit tortuous, to be honest, but what we can do first of all is pull this lambda out into its own variable. So that's the block that we're applying in our map. Now we want a block that represents this parallel map stream, and a good way of doing that is just to call run here. If we introduce run, that behavior is the same, but it means that we've got a variable here that we can pull out. And we'll call that our map function. Okay, now we'd like to pull that up here to the top, but we can't because it still depends on this f. So we need to introduce this f as a parameter to our lambda. Now, unfortunately, you can't do that directly. We can't say introduce parameter here, because if we do, IntelliJ looks out to the nearest function scope, which is our test, not a lambda. We can solve that problem by making this into an anonymous function. And now we can introduce a parameter to that. Now you notice this is broken. It's broken because IntelliJ hasn't added the parameter to the type of the variable here, but we can solve that problem just by removing that. And also it hasn't introduced the parameter here, but in fact this is now just input with the map function applied to f. And we can check that's true by running the tests. And they pass. Now we can inline this f, its work is done. And now the point of this was to move this map function here up to the top. And again, we'll run the tests. Now this anonymous function is a bit of a mouthful. Its work is done, so we can convert it back to an expression, a lambda. But that doesn't work because we don't have enough type information. Let's undo that. If we specify the type explicitly here, then we can convert this to a lambda. Now what this blockAt is doing, I don't know. Actually required. And then if we look at this, it takes a function which is string to int, and the receiver, which is our list of string, and applies that to ParallelMap stream. So in fact, overall, we can remove that, and we're left with just a lambda. Now what we should be able to do is to take all this code here and make a function out of it. Now IntelliJ warns that this map function won't be accessible after the extraction. Sometimes it lies, let's have a look. But in fact it has messed up entirely. I don't know why this is just a val. It's unable to make that refactor work properly. I don't see why a value of a function is any different than the value of an int, but it evidently isn't happy. So let's undo that. And what we can do is we can take all of this, make it into a function. And this is check and time. So it's going to do the check and it's going to return the time. And now, in fact, we can take this and make a parameter out of it. So this is our map function. And you see here then that check and time, we just pass it a lambda that says ParallelMap stream in this case. And that means that up here we can do the same thing. So we could replace all this code with that, where this is not ParallelMap stream, it's just map, the one on iterable, and run that. Good. So now we know we're running the same tests on our two implementations, and we can add another one. Okay, just for kicks, I'm going to write a threads version. This is going to create a new thread for every item in the map. Remember that our basic operation is to say this.map it. Okay, let's dive into this. What we're going to do is instead of calling map directly, we're going to map into a new thread. Let's take a while to compile. So we're going to create a new thread, and Kotlin concurrent thread creates a started thread. I'm going to do our computation on that thread, and our computation is this it up here. Let's call that f up there. So on our thread, we're going to call f on it, where it is the item in the list at the moment, this one here. Now, having set all those threads off, we need to wait for them to finish, and that's a join. So we'll map here into thread, and we're going to do thread.join. If we do that, by the time we exit here, all of our calculations will have been done. We just will have lost them. They disappeared here because we didn't assign that to anything. So what I'm going to do is I'm going to give us somewhere to put that, and I'll call that result, and I'm going to make that an atomic reference of, in this case, the int that's coming out. That will be unpopulated to start with. And why an atomic reference? Well, to be honest with you, I'm not sure it needs to be an atomic reference. It just needs to be something we can mutate once we've got the value. Atomic references propagate state properly across threads, so it seems like a good idea. Okay, so once we've got the result, we're going to put it into that atomic reference. How are we going to transmit it between here and here? Well, the answer is that we can create a pair of the thread and the result in our map. And now in this lambda, we'll be getting not just a thread, but a thread and a result. And we want to join the thread and then get the value out of the result. And lo and behold, that compiles. Does it work? Well, let's run it. We see not only did it work, but it works really quickly. So it was only 72 milliseconds, and the fastest it could have been is the 50 milliseconds that we're actually waiting for one of those things to finish. In that 72 milliseconds, we've created and started 100 threads. So people say that threads are slow, but this is pretty quick. Now in order to extract our function from our test code, we should be able to take this whole lambda, make it into a variable, make that variable into an anonymous function. And then if we just give that a name here, we can take it out of here, call it in here, and finally paste it in here. Mess that up slightly. And now we can introduce our types. And one for the int. Finally, make this expression body and maybe lay it out a bit better. And a little mess up of a refactor there from IntelliJ. Good. Now the threads version may be quick, but if we were to ask it to run on 100,000 items, then we get 100,000 threads. And I suspect that wouldn't be so quick. The solution to that sort of thing is to use a threadpool. So let's write a threadpool version. So for our threadpool version, we're going to need a threadpool, and that is executors new fixed threadpool, and we'll maybe give it 10 threads. We'll play around in a minute with what difference that makes. And now we want to submit tasks to that threadpool. So we're going to map, instead of calling the function, which I think before we go on, we'll rename to f. Instead of calling the function, we are going to go to the threadpool and submit a callable. And a callable will be invoked later and remember its result. So this callable is what's going to call the function on it. Now, when you submit a callable, what you get back is a future. So having submitted all these, we can then map over those futures, and on a future, we can call get. And get will wait for the future to complete, which is say, wait for this callable to be run, and then return what's in it, which is the result of calling our function. And it will block until that's ready. So it's the same as the block we did here where we did thread join, but the future is looking after it for us. And you see that compiles, so there's a good chance that it will work. Let's have a go. Run the tests. There we go, and let's have a look. And so our threadpool version took half a second, our parallel stream version 758, and our threads version 72. Take these all with a pinch of salt, but they give you some idea for the relative times involved. And given that the threadpool version is completing in half a second rather than 5 seconds, we know it is running in parallel. And again, it's passing all the tests, so with reasonable confidence that its behavior is right. Let's just pull our utility function out of this by extracting a function of this, which is ParallelMap threadpool. And you can see hopefully that takes the threadpool we want to run the things on. Take this out of here, move it down to here, make it public, and introduce the types. And make it look like the one above. And remove the offending type argument, and run. So now we can see that our Kotlin version takes the at least 5 seconds that happens if we run them in serial. The parallel stream version, 755, it's a lot quicker, maybe good enough. The threads version runs really quickly, but at the expense of potentially killing the machine by creating too many threads. And the threadpool version, well, that's quicker than anything but the thread version at about 10 times speed, because we had a threadpool of 10 items. So let's see whether we can scale that. If we change that to 50 and run, and it comes down to 200 milliseconds. So there's evidently some overhead, but we can make it quicker by throwing more threads at it. And now finally, the version that all true-blooded Kotlin programmers have been waiting for, the Coroutines version. We'll start again with plain old map. And being coroutines, we need a run blocking call in order to wait for them to finish. I should say, by the way, that run blocking and most of the structured concurrency is in Kotlin X coroutines, so we've had to import that in our Gradle file. Got a version that looks like it's a Kotlin version, but isn't. In fact, by the look of the GitHub page, it originally was a Kotlin version, but it hasn't had to be updated for the newer versions of Kotlin. That certainly confused me for a while. We'll follow roughly the same pattern here as we did for threads. So we'll map with a block that runs something async, and that async is going to be our function on it. Now async returns a deferred. So here we have a list of deferreds, and there is an await all on list of deferred. So let's try that. Well, that's passed the spec for our map. But what it hasn't done is run any quicker than the serial version. So something is amiss. Looking through the documentation, it turns out we need to run this in a coroutine scope. Now, coroutine scope defines a block in which if any of these async calls fail, it will abort, and we'll also run them in parallel. Let's try again. Still no good. Now, the reason that doesn't work took a bit of research. If we look at what we're actually doing in here, we're doing a thread sleep and then returning the length. If we were to do something more coroutine compatible, which is to say, call delay for our 50, followed by it.length, and run that, then we would indeed run in parallel. It turns out that if we want to do something like thread sleep, which actually blocks a thread, then we need to run our coroutines in a thread pool. In order to do that, we can pick up this thread pool here and use it in our run blocking call as a coroutine dispatcher. Then we can return this to thread.sleep, and we still get our concurrency. So now we can just return this to our on it and extract from here this as our parallel coroutines. Now that doesn't compile for some reason. IntelliJ seems to have been confused by this scope, but we can solve that by making it a single expression, I think, that's actually returning the right thing. There we go. And once again, we will refactor this to make string our t and int our r. And once again, there's a little tiny break here. I messed that up. Take this out of here and add it to our implementations. Now note this is a suspend function, which means we have to run it in a coroutine context, and it is liable to be suspended. Also, it would make sense if this function was suspendable as well. And we just add that in there, and that doesn't affect the fact that we can pass a non-suspending function to it. Run all those tests for one last time. Good. Okay, there we go. Just about fitting on the screen, we have 4 different ParallelMap implementations. You can see the ones we wrote by hand ourselves, the last 3, all follow the same sort of pattern. We map over starting something asynchronous and then I'll wait for them all to finish and get the results out. Which one should we use? Well, I don't know yet. In my years of programming, I've discovered the devil is in the detail, and I suspect the detail here is how they act when there are errors. So before we actually pick one, we should investigate how they behave when things go wrong. If you'd like to see that investigation, then please subscribe to the channel. And if you enjoyed this, then I think you'll enjoy both the workshop that Nat Price and I are running at Kotlin Conf in Amsterdam next year, and also the book that we wrote together called Java to Kotlin, a Refactoring Guidebook. Details of both of these are in the show notes below. Thanks for watching.